So now we prove the following lemma. So recall that our goal is that when we have a d-regular digraph T, we want to decompose it into digraph T1, T2 to say Ts and D0, so that all of this has large girth. And how do we want to do it? And also, this is almost regular. So that we can actually apply this lemma to each di. However, in order to apply this lemma, we need to make sure that each di is actually regular graph, t-regular digraph. But this is almost regular, we can add some edges to make it exactly regular, which will increase the degree, but but the statement we want to prove has an additional error term, which so that adding some edges, increasing d to say d plus some number is not too bad. So this is our goal. We want to decompose this into several graphs with large girth and almost regular, and then one graph which might have much less number of edges. This is also close to regular, but the degree is much smaller than d. Then this we kind of arbitrarily partitioned it into several linear forest, and then this we apply the previous lemma. But how do we want to do it is that if we have graph G, we color the vertices by either 1 to some number, say S. Let's write P. So that if we have this edge from vertex V to U, and if V is colored with some number I, some number A, and U is colored with some number A plus I, then we distribute this to the digraph DI, because difference between these two is I. Then in DI, if we have a cycle, let's say this P is prime, and and we decompose into T1 to Tp minus 1. Every time, if this is colored with A, and this must be colored with A plus I, this is A plus 2I, and so on, A plus S minus 1I, and A must be same as A plus S times, no, S times I. Say you take everything into modulo P. So if I is between 1 and P minus 1, which is not P, then this ensures that S is to be divided by P. So if we somehow use vertex coloring, where the colors 1 to, say, P, and then decompose the edges depending on its end vertices color, and if the difference between these two is I, say modulo P, everything is modulo P, then you add to Di, then you can make sure that these actually have a girth bigger than or equal to P. So that's roughly what we want to do. But wait. Yeah. That can ensure large girth, but we also want to make sure that it is almost regular. So to ensure this, we want to color the vertices with random coloring. So the following lemma ensures that we can actually achieve that each such graph is almost regular. So let D be sufficiently large and capital D be a deregular digraph. And let P be a prime number between 10 square root of D and 20 square root of D. It doesn't have to be prime at this lemma, so let's say that's just an integer between those two. Then we want to show that there exists P coloring of the vertices of D by the colors in P bracket P. So we color the vertices by using the colors from 1 to P, satisfying the following. So for each I and vertex V, the number of out neighbors or in neighbors of V with color I is D over P plus minus say 5 times square root of D log D over P. So see that this number is expectation. If we color the vertices with P colors at random, then this is expected number of out neighbors of V with color I, or in neighbors with V with color I, for any I and V. But this is the error term. So let F be a random vertex coloring of V, which is obtained by choosing the color of each vertex independently and random. Independently, uniformly at random. And for each V and I, let A plus V I be the event that, say, as the number of out neighbors of V with color I is not this. As this X is binomial random variable, what I mean is that we have V and you have the D out neighbors, and each one of them has one of the numbers in P. So this has color I with probability 1 over P. And these random variables, this has color I, this has I, this has I, those random variables, indicator random variables, are all independent. So we can apply the Cherenkov bound, which we showed last time. So for each out neighbor of V, we consider this independent random variable which is 1 if the chosen color is I for the vertex, which happens with the probability 1 over P. And then if it is 0 if the color is not I. Then you can apply this Chernoff bound. So probability of A plus BI is that it's at most 2 times e to the, you apply this, minus, you scale this, 25 d log d over p over 4 times pn. What's pn? Pn there is this 1 over p probability, there are d random variable. So 4 times d over p, which is strictly smaller than 1 over say d to the 4. Because dp are gone, then this is roughly 2 to the e to the negative say 6 log d. So this is smaller than that because d is sufficiently large. Similarly, we define A minus bi, which also happens with probability smaller than 1 over d to the 4. So if we have an event, let's say this event, then this is mutually independent of all events, say A plus uj or form of A minus uj for all u that do not have a common neighbor in the underlying graph of D. So we have V, and you consider out neighbor or in neighbor. So in that case, then if we have some vertex U which also has out neighbor or in neighbor there, then this event actually can be determined by the colors of this. So by the, however, if we have a W which doesn't share any whose out neighbor or in neighbor are not intersecting with these, then by mutual independence principle, this event only depending on this each of gi, which is independent random variable which gives a color on the vertices, and it depending on these colors or this color depending on you are taking plus or negative. But these events are not related to these independent random variable. So all those events where W is not sharing any common neighbor in the underlying graph of D with V, they are, this event is mutually independent of them. And how many such vertices are there? So each V has a 2D out neighbor. Okay. So for this, it has a D out neighbor, and then it has a 2D, D other out, each of them has D other out neighbor and D other in neighbor. So it has 2D square many other vertices, which shares the vertices in here. So if we consider this, then the in neighborhood of this is not really relevant. So from here, and you take other 2D mode events from each of the vertices. And the choice of I or J here is P. So altogether, the dependency digraph for those events has max degree and most 2D square P. And what do we know? The natural base of the log times the probability of bad events time this. So P is roughly square root of D. So, and D is large. So this is roughly D to the 2.5. And this is D to the 4. So we have a D to the 1.5 on the bottom and then some constant here, but D is sufficiently large. So this is smaller than 1. So by robust local lemma implies that with positive probability no events A sub vi plus or A sub vi happens. None of the such events happen, and this provides the desired coloring F. So this proves the lemma. Now we prove the desired result. So let's say we have a D-regular digraph. And pick a prime number P between 10 square root of D and 20 square root of D. So by Bertrand's postulate, we know that for any number x and 2x, for any number x bigger than say 2, we can find the prime between x and 2x. And by using the previous lemma, we find the vertex coloring. Satisfying the conclusion of the lemma. And for each I, let Di, as we plan, be the spanning digraph. Spanning subdigraph of D with edges UV, where f of v is f of u plus I modulo p. Then, what does the previous condition become? This condition actually translates into that each di forms a digraph such that all vertices have in degree and out degree d over p plus minus 5 square root of d log d over p. So it's not too deviated from d over p. Moreover, for each I between 1 and p minus 1, each di has curls p, curls at least p. As all cycles in di has length divisible by p, as we noticed before, the f value of this vertex is a, and f value must be a plus I modulo p, and so on, a plus I s minus 1 modulo p, where this is cycle as length s. Then a and a plus is must have same in modulo p, which means s is divisible by p. So now we have this, and one can add, vertices and edges to each vi to actually make it converted into say di regular digraph t prime I of course at least p where ti is 5 times square root of d log d over p. So this is basic proposition in graph theory that we have learned. Yeah, we will not actually prove it here, but yeah, it can be. It's not so difficult to actually do this, so you can think about it by yourself. And once we have this, the previous theorem implies that each d prime I actually decompose into at most di plus 1 directed linear forest. And what's dp? dp actually again we use the trick as the give me a moment. Yeah, again we can add some edges to make this TP as a regular digraph, and then we use the trick that we use the whole theorem. By using the same trick, we can actually decompose this into d over p plus wait a moment. Yeah, so this decomposes into this many plus 5 square root of d log d over p digraphs with maximum in and out degree and most 1. And each such graph actually decomposes into 2 directed linear forest. Because this such a digraph is disjoint union of directed cycle and directed paths. Once we have that, you just cut the cycle into 2 directed paths. So you take one such a directed linear forest and then the other one. So each one of them actually, decompose into 2. So let's write that as each one decompose into two directed linear forest. dp actually decomposes into two d over p plus 10 square root of d log d over p digraph. Directed linear forest. So in sum, how many directed linear forests does D decompose into? You have p minus 1 times d over p plus 5 square root of d log d over p plus 2d over p plus 10 square root of d log d over p plus say p minus 1, because here I forgot to write 1. So altogether, because p is between 10 square root of d and 20 square root of d, you can compute that this is just nothing but the d plus big O of d to the 3 over 4 log d square root. So this proves what we wanted. And in next video we will talk about some slight generalization of the local lemma that I mentioned before, which is called lopsided local lemma.